In episode 102, titled Activation Functions, ReLU, Sigmoid, Tanh, Softmax, and Output Behavior, we focus on the idea that neural networks only become powerful when you give them nonlinear switches. Without activations, a network is essentially a stack of linear operations that collapses into one linear transformation, no matter how many layers you add. Activations are what allow layered feature building because they let the network bend, gate, and reshape signals as they flow forward. On the exam, you are expected to recognize the common activations, what kinds of outputs they produce, and how they affect training behavior in a conceptual way. This topic is not about memorizing equations, but about understanding which activation belongs where and why certain choices are common. When you can match activation to task, you reduce a lot of confusion around network outputs, and you prevent mistakes that are surprisingly easy to make. The goal here is to see activations as engineering tools that shape behavior, not as mysterious ingredients. Before we continue, a quick note. This audio course is a companion to the DataX books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyber.author.me in the Bare Metal Study Guide series. An activation function is the function applied to the neuron's weighted sum after adding the bias to produce the neuron's output signal. The weighted sum is the linear part, and the activation is the nonlinear shaping step that determines what range of values the neuron can output and how sensitive it is to changes in input. This shaping matters because it influences what kinds of patterns the network can represent and how gradients flow during training. You can think of the activation as defining the neuron's response curve, meaning how it reacts when the weighted sum is strongly negative, near zero, or strongly positive. Some activations squash outputs into a limited range, while others allow unbounded positive outputs, and that choice affects both representation and stability. The activation is therefore not decorative because it changes the network's function class and its trainability. Once you understand activations as response curves, the rest of the choices become more intuitive. Rectified linear unit, commonly called ReLU, is widely used for hidden layers because it is simple and it tends to support healthy gradient behavior in many practical architectures. ReLU outputs 0 when the input is negative and outputs the input itself when the input is positive, creating a piecewise linear response that is easy to compute. This simplicity often translates into faster training because gradients do not shrink as aggressively in the positive region as they can with squashing activations. ReLU also encourages sparse activations, meaning many neurons output 0 for a given input, which can act like a form of implicit regularization and can make representations cleaner. Because it avoids some of the saturation problems of older activations, ReLU became a default choice for many hidden layer designs. The key idea is that ReLU is common in hidden layers because it combines computational simplicity with generally stable gradient flow. Sigmoid is an activation that squashes inputs into a range between 0 and 1, which makes it a natural choice when you want an output that behaves like a probability for a binary outcome. In some architectures, the final layer uses a sigmoid to convert a raw score into a probability-like value for the positive class. This aligns with binary classification logic because the model can output a single number interpreted as estimated likelihood under the model's assumptions. However, sigmoid is less commonly used as a hidden layer activation in modern deep networks because it saturates, meaning it becomes very flat for large positive or negative inputs. When the activation is flat, gradients become very small, which slows learning and can make training fragile, especially in deeper networks. Even so, sigmoid remains a useful output activation when the task is binary classification and the architecture expects a single probability output. The exam expectation is to recognize sigmoid as linked to binary probability-style outputs rather than as a default hidden layer choice. Tanh, short for hyperbolic tangent, is another squashing activation that maps inputs to a range between -1 and +1, producing outputs that are centered around 0. This centered property can be helpful because it can make optimization behave more symmetrically than sigmoid, which is centered around 1/2. Tanh was historically popular in hidden layers because it often trained better than sigmoid in earlier network designs, especially when depth was modest. In modern deep networks, Tanh is less common for hidden layers because it still saturates, meaning it can slow learning when inputs push the neuron into extreme regions where the slope is very small. That said, Tanh remains conceptually important because it illustrates how centering outputs can affect signal flow and how activation choice shapes the internal representation space. In some architectures and in certain recurrent designs, Tanh still appears because its bounded, centered behavior can be useful. The practical takeaway is that Tanh can help when you want centered activations, but it is not as dominant as ReLU in many contemporary feed-forward hidden layers. Softmax is used to produce a multi-class probability distribution across classes by taking a vector of raw scores and converting it into non-negative values that sum to 1. Unlike sigmoid, which produces one probability for a binary decision, Softmax produces a set of probabilities, one per class, where increasing the probability of one class necessarily decreases the probabilities of others. This is appropriate when classes are mutually exclusive, meaning the correct label is exactly one class out of many. Softmax is therefore commonly used in the output layer of a multiclass classifier, where you want a probability-like distribution that can be interpreted as the model's relative support among competing classes. The output behavior matters because it aligns directly with decision rules, such as selecting the class with highest probability. Softmax also supports calibrated style reasoning in some settings, though calibration still must be validated rather than assumed. The exam expects you to recognize Softmax as the multi-class output activation that produces probabilities that sum to 1. Saturation issues are an important conceptual point because they explain why sigmoid and Tanh can slow learning in deep networks. When an activation saturates, its output changes very little even when the input changes, meaning the derivative is small and gradient signals weaken as they backpropagate. This can lead to slow convergence and difficulty training deep models, especially when many layers push signals into saturated regions. Saturation is not purely theoretical, because it shows up in practice as training that stalls or proceeds extremely slowly unless initialization and scaling are carefully controlled. ReLU avoids saturation in its positive region, which is a key reason it often trains more efficiently, though ReLU has its own issues that require monitoring. Understanding saturation helps you explain why some activation choices are historically important but less common today for hidden layers. It also reinforces that activation choice is connected to training stability, not just to output ranges. Matching activation to task is one of the most practical skills because output behavior must align with what you are trying to predict. For regression, the output is often a linear activation, meaning no squashing, because you want the network to produce values across a continuous range, and you want the loss function to shape the scale appropriately. For binary classification, a sigmoid output can be appropriate when you want a single probability of the positive class. For multi-class classification with mutually exclusive labels, Softmax is typically appropriate, because it expresses competition among classes and produces a probability distribution across them. This mapping is not about tradition.
It is about ensuring the model's output space matches the semantics of the problem. Misalignment here leads to confusing outputs and poor training signals, even if the network has plenty of capacity. At exam level, being able to choose the correct output activation for each task is a core competency. A classic misuse is applying softmax when labels are independent rather than mutually exclusive, because softmax forces probabilities to compete and sum to 1. In multi-label classification, where multiple labels can be true at the same time, each label should be modeled with an independent probability output, often using separate sigmoid outputs, because the presence of one label does not require the absence of another. Softmax would incorrectly tie labels together, making it impossible for the model to assign high probability to multiple labels simultaneously. This matters operationally because it directly affects what predictions the model can express, not merely how you interpret them. The exam often tests this distinction by describing scenarios where multiple categories can apply at once, which should trigger the idea of independent outputs rather than a competing distribution. Avoiding softmax in that situation is therefore a correctness issue, not a style preference. Recognizing label structure is as important as recognizing activation names. Activations also connect to gradient flow and training stability because their derivatives determine how error signals propagate backward through the network during learning. If gradients vanish, learning becomes slow because early layers receive little signal about how to adjust. And if gradients explode, learning becomes unstable because updates become too large and training diverges. Activation choice interacts with initialization and scaling to influence whether gradients remain in a healthy range. ReLU often helps with vanishing gradients compared to Sigmoid and Tanh, but it can create its own issues, such as neurons that stop activating if they consistently receive negative inputs. Tanh and Sigmoid can be stable in shallow settings, but can become difficult in deeper settings without careful design. Thinking of activations as gradient shapers keeps you focused on trainability rather than on names. At exam level, the key is understanding that activation choice affects whether training signals move effectively through layers. Activation choice should be communicated as an engineering decision rather than as magic, because it is a controlled design choice with predictable effects on output ranges, learning dynamics, and interpretability. When stakeholders ask why a network uses a particular activation, the correct explanation ties to what the output needs to represent and how the model trains reliably. For example, you choose Sigmoid when you need a binary probability output, and you choose Softmax when you need a multiclass probability distribution, not because those choices are trendy. For hidden layers, you choose ReLU because it is computationally efficient and often supports stable training, while acknowledging that it is one option among several and that alternatives exist depending on architecture needs. This framing builds trust because it shows the model is designed intentionally rather than assembled by guesswork. It also supports governance because design decisions can be documented and reproduced. Treating activations as design controls makes neural networks feel like engineering systems rather than mysteries. Monitoring outputs matters because activations can cause practical failure modes such as dead neurons or unstable scaling that degrade learning and performance. With ReLU, dead neurons can occur when a neuron's inputs remain negative for most cases, causing it to output 0 consistently and stop contributing meaningfully to learning. With Sigmoid and Tanh, unstable scaling can show up as saturated outputs that cluster near extremes, producing weak gradients and slow learning. In output layers, activation mismatches can create probability distributions that are overly confident or nonsensical, which can harm calibration and decision thresholds. Monitoring includes looking at activation distributions, training curves, and validation behavior to ensure the network is not stuck or collapsing into degenerate behavior. This is not over-monitoring, because networks can fail silently while still producing numbers that look legitimate. A disciplined approach treats activation behavior as part of model health, not as a one-time architectural choice. The anchor memory for episode 102 is that ReLU is for hidden layers, Sigmoid is for binary outputs, Softmax is for multiclass outputs, and Tanh is for centered outputs. This anchor is not meant to be absolute, but it captures the common pattern that resolves most exam questions quickly. ReLU dominates hidden layer design in many modern feed-forward networks because of training behavior. Sigmoid remains a useful final activation when you need a single probability for a binary decision or independent label probabilities. Softmax is the standard choice when classes are mutually exclusive and you want a distribution over classes that sums to 1. Tanh remains important conceptually and can be useful when centered, bounded outputs are helpful, even if it is less common now in many hidden layer stacks. Keeping this anchor in mind helps you choose activations correctly without drifting into unnecessary detail. To conclude episode 102, titled Activation Functions, ReLU, Sigmoid, Tanh, Softmax, and Output Behavior, choose an activation for one task and explain your reason in operational terms. For a multiclass classifier that assigns each input to exactly one category, Softmax is the appropriate output activation because it produces a probability distribution across classes that sums to 1, matching the mutually exclusive label structure. In hidden layers for that same model, ReLU is a sensible choice because it is computationally simple and often supports stable gradient flow in deep architectures. If instead you were building a binary classifier with a single probability output, Sigmoid would be the natural output activation because it maps to a value between 0 and 1 for the positive class. This reasoning shows that activation choice is about output semantics and training behavior, not about preference. When you can tie the activation to the task and to stability, you demonstrate exactly the level of understanding the exam is designed to test. Thanks for listening. For more audio courses, daily newsletters, and more, please visit BareMetalCyber.com.